Okay. So, got a lot to get through today. Let's see how much we can power through and how quickly. Only a few technical glitches today. I hate my laptop. In any event, heat versus temperature. This is a distinction that I feel it is necessary and helpful to make. Thermal energy, heat, and temperature are all different things. They cover different topics, but they all sound very similar. We use them in very similar ways. Thermal energy is the energy contained in an object or a substance or a system, however you want to call it. It is the energy of the random motion of the particles of the system. Okay? So remember, particles are always in random motion. Okay? They're always bouncing around. Okay? In a solid, they're moving very little. They move more in a liquid. They move a lot in a gas. Regardless, they're always moving. Temperature is the measure of that random kinetic energy. It's the measure of the average. Okay? So at the same temperature, the particles of two different objects will have the same average random kinetic energy. Okay? They'll have different thermal energies depending on what substance they're made of and how much there is of each substance. Okay? But they'll have the same average. So thermal energy is measured in joules. Temperature is going to be measured in Celsius or Kelvin or what have you. Okay? They're very, very different things. Heat is a measure of transfer. Okay? It is the transfer of thermal energy from one system to another. So when you have, if you put a piece of ice in a hot coffee, then you'll have thermal energy transferring from the coffee to the ice. That will be the heat, the transfer of energy from one to the other. Okay. So thermal energy is the total energy of that random motion. Temperature is the average. Heat is the transfer. So a very small, very hot pebble will have a higher temperature than a big cold boulder, okay? Because the particles of the pebble are just moving faster on average. But the boulder, nevertheless, will probably have more thermal energy just because it has more particles. We tend not to care too much about thermal energy. It's important, it's there. We work with temperature and heat. We talk about the transfer of thermal energy a lot more than we talk about thermal energy itself. And when we think about thermal energy, we're mostly thinking about it in terms of temperature. So how does thermal energy move? How are we going to get that transfer of heat? Well, this is, going straight back to your middle school science, possibly. First up, we have conduction. Conduction is just through direct contact. Okay? Object A touches object B, and thermal energy moves from one system to the other. So you touch the stove, you burn your hand, that was conduction. You put the ice in the hot coffee, the ice gets heat directly from the coffee through conduction. Convection is the movement of heat through the movement of matter. That is to say, matter moves from one place to another and thus brings its thermal energy with it. We typically think about this in terms of, you heat something up and thus you get the hot stuff moving away from where it was. So, a hot air balloon, that is an example of convection. The air inside the balloon is hot, it's less dense, and therefore it rises into the air. Okay? If you look above a fire, you see the wavy lines, the shimmering in the air. That's because the air above the fire is being heated, and it is rising. Okay? So it's less dense. You get oddities there. Okay. So convection is the movement of heat via the movement of matter. Okay? So conduction, heat moves, matter doesn't. Convection, matter moves and takes heat with it. Radiation is when you have the movement of energy by means of light. So there's no physical contact with radiation. With conduction, there is. Okay? So when you hold your hands in front of the fire, you are not touching the fire. You are not, you don't have your hands above the fire. You're in front of the fire. You still feel heat. That's because there's a lot of radiant energy, light coming off of that fire. Okay? Above it would be convection. In it would be conduction. So those are 3 different ways for thermal energy to be transferred from one place to another. For the purposes of this class, what we'll mostly be dealing with is going to be conduction when we do calorimetry. All right, and that's it for that particular set of slides. That is a nice short set of slides. So let's go ahead and move on to work. Specifically, expansion work. So, work is force applied in the direction of motion, okay? Which is a little bit complicated. If you push something along the ground, you are doing work. Okay? You are using force. You're applying that force in the direction that the object is moving. Okay? If you were to push an object so that it slid along a frozen pond, you would do work initially to get it to start moving, but once it's moving, it's just sliding. You don't have to put any more force in. You're no longer doing work. Okay? So force in the same direction as the motion. That is the simple physics definition. And that works when you're talking about choo-choo trains. It doesn't work quite so well when you're talking about chemicals and chemical reactions. Because chemicals, that's not ropes and pulleys and so on. Chemicals is explosions. It's billions and skajillions of particles operating randomly. So chemical work, we have to be a bit more clever about that. So instead, we talk about it in terms of pressure. We will get into pressure more in Chapter 9. But for now, know that all fluids exert pressure. Okay? Fluid means a gas or a liquid. A fluid is anything that can flow. Okay? So a gas is a fluid. A fluid will exert pressure on its container or anything submerged in the fluid. So anything that holds the fluid, anything that is in the fluid, will feel pressure from that fluid. Okay? You are experiencing about 101,325 pascals of pressure from the air around you right now. You're not aware of it just because you're always experiencing that pressure, and also because you are also full of fluids, mostly blood and lymph and poo. And that pushes back against the atmosphere around you. Okay? So air does exert pressure. We experience that all the time. We're largely not aware of it, but, it's there. Okay? And that's just because there is, an entire atmosphere sitting on you right now, exerting that pressure. So the units of pressure is the Pascal. 1 Pascal is 1 Newton per square meter. Okay, pressure is force over area. So the force of some object, or in this case fluid, pushing down on whatever area you're talking about. The units of force are the Newton, as we've already discussed. The units of area are the square meter. Okay. So 1 Newton is about the weight of 1 apple. 1 square meter is the top of the washing machine. Right? So 1 apple spread out over an entire washing machine. So imagine you take the apple and you make applesauce and you spread it out over the entire washing machine. That's not much. That's a very small amount of pressure. Hence, the entire atmosphere pushing down on you is 101,325 pascals. That's 101,325 apples sitting on a washing machine. Yeah, that's much more significant. Okay. However, pascals, it ends up being fairly inconvenient because the pascal is just so small. So we tend to work in atmospheres, where 1 atmosphere is, by definition, 101,325 pascals, or 101.325 kilopascals. We also have the bar, okay? Where baros just means pressure. So 1 bar is exactly 100,000 pascals. That is much more convenient for engineering work. It's a nice round number. So you find that fairly commonly. That's a popular one. So 1 atmosphere is 1.01325 bar. You are going to have to be able to do conversions with this. Okay? Be able to convert between atmospheres and pascals. So what is 0.8293 atmospheres in pascals? Let's go ahead and do some conversions. Let me get my calculator up. All right. 0.8293 atmospheres in pascals. So one atmosphere is 101,325 pascals. So 0.8293 atmospheres is 84,028 point. Let's see, we got, so it's going to be 84,030. Remember, sig figs. Don't forget your sig figs on the test. They'll probably be douches about that. All right. So next up, what is 231.1932 kilopascals in atmospheres? So 231.1932. So kilopascals means we have to multiply by 1,000. And then to convert that to atmospheres, we divide by 101,325. So 231.1932 is 2.2816170 atmospheres, about 2¼ atmospheres. You would feel that pressure. That would be like being under a couple feet of water. You'd notice it. And what is love? Baby, don't hurt me. All right. So pressure. How do we experience and change in pressure? Changing pressure means changing force or changing area, because pressure is force over area. So you can increase the force, going from mouse to elephant would be one way of changing pressure. You would increase pressure significantly, going from a small force to a big force. But you can also change pressure by changing the area that you're exerting that pressure over. That is what snowshoes do. They dramatically increase the surface area that you're walking on. Damn it, cat. Just stole one of my socks. Dramatically increases the surface area, decreasing by a lot the pressure that you exert on the snow, making it easier for you to walk through snow. And don't ever let somebody walk on ice in high heels, because they will go right through that ice. Because way, way less pressure, or sorry, way, way less area means way, way more pressure. Okay. All right. So, pressure is equal to force over area, meaning that force is equal to pressure times area. Weren't we talking about work? Yes, we were. Remember, work is force times distance. So this is how we are going to be able to get to work. Because when we talk about work in chemistry, we're often talking about pressure work, expansion work, as it's called. You have a gas that changes volume. So work is equal to force times distance. But as we saw earlier, just right here, force is equal to pressure times area. So work is equal to pressure times area times distance. Area times distance, that's a volume. So when you have a gas changing volume, you have something doing work. Now, be very, very careful about this. That negative sign is super duper important. Okay? It's negative P delta V. Because remember, we chemists, we are decent human beings. We are moral. We care about the system, not the surroundings. So when a system expands, the system is doing work. So it is losing energy in order to do that work, to expand outward against external pressure. Okay? It's doing work, it's losing energy. So work has to be negative when the system expands. When the system is compressed, some external pressure is doing work. Okay, it's forcing the system to contract, to become smaller. So the work is going into the system in that case. So work has to be positive. So when the system is expanding, it's getting bigger, and delta V is positive. When the system is being compressed, it's getting smaller, and delta V is negative. So in order for P delta V, P times delta V, to match the sign convention that we have set up, where we care about the system, we have to have that negative sign. That negative sign is important. If you don't have that, then you'll get the sign wrong, you'll get the problem wrong, and your parents will be very disappointed in you. Not angry, just disappointed. So be careful about that negative sign. Don't lose it. Don't forget it. So the reason we're talking about this is largely because of pistons. In the 18th century and 19th century, physicists loved steam engines. They were the workhorse of the 18th and 19th centuries. They were powerful, they drove the world forward, and they depended upon changing volumes in gases. And they wanted much more efficient, much more powerful steam engines. So in order to do that, they needed to really understand how expanding gases did work. So that's why we talk about this in these terms. You have your gas inside the cylinder, expanding outward, pushing on the piston, doing work in order to drive the locomotive forward. Okay. So that is why we talk about it in these terms. So, some simple math, relatively simple math. Okay. What is the work done by a system that expands from 101.25 milliliters to 125.75 milliliters against a constant pressure of 1.225 atmospheres? Okay. This is a somewhat mean problem because the units don't match. Okay. Work is measured in joules, which is based on the base units, newtons, cubic meters, things like that. In chemistry, we don't work in newtons or cubic meters or square meters or anything like that. We work in units that are convenient for us there in the lab. We work in atmospheres. We work in milliliters. So this problem, in addition to talking about work, also talks about the conversions that are necessary for work. I don't know if they'll ask you this on the test, but they could, and it's good practice. So let's bring the calculator back up. So the system is expanding from 101.25 mils to 125.75 mils. So we're doing some subtraction. 125.75 minus 101.25. So 24.50 milliliters change. It's expanding, so that's going to be positive. Constant pressure of 1.225 atmospheres. So 1.225 atmospheres is how many pascals? You multiply by 101.325, 124, 123.125. All right. We also need to convert from milliliters. We have 24.5 milliliters right here. We need to convert that to cubic meters. So 24.5 milliliters, you divide by 1,000, 0.0245 liters. And then we convert that to cubic meters. 1 liter is 10 to the negative third cubic meters, so that means we divide by 1,000 again. Okay. So this is our change in volume in cubic meters. And this right here, the 124, 123.125, wow, that's, is our pressure in pascals. So now we can, we can whatchamathing, we can doobly-doo, we can thingamabob. We can multiply in order to get it into joules. So 0.0000245 times 124.123.125, 3.041 joules of work. Okay. So that's one way to do this. A slightly simpler way is to do 24.5 milliliters, convert that to liters, multiply that by our atmospheres, 1.225, and that gets us work in liter atmospheres. And then 1 liter atmosphere is 101.325 joules. So we multiply this by 101.325, and that also gets us the 3.041. Okay. Probably easier to just remember this conversion down here on the bottom, where liters times atmospheres gets you a weird unit of energy, the liter atmosphere, which you can then convert to joules as 101.325. Or you could do the slightly or easier to understand route that involves two conversions. Convert atmospheres to pascals and convert liters to cubic meters. Either way, you're going to have to convert from milliliters to liters. Okay. You're going to have to be very careful of your units moving forward. Units are big juju. Lots and lots and lots of important. So 3.041 was our number, but we also have to pay attention to the sign, okay? Because the system is doing work, it's expanding, meaning that that number should be negative P delta V. Okay? Meaning that the actual answer is negative 3.041 joules of work. It's doing work. It's expanding. All right, and I will leave that problem, number 2, as an exercise for you to do at home. Just be aware you're doing work on the system, so that number should be positive for number 2. All right. So I'm going to take a quick break, rescue my sock from the cat before he gives it to the dog and lets the dog destroy it. And I will be back in 10 minutes to continue today's lectures.